So again, there's different ways you can do this, but this would definitely get you there. I'm using string length, so I need to include string.h, and then define your function, takes a car pointer, returns an integer. So I initialize a running counter to 0, that's C, and then the for loop is sort of a standard way to march through each character of a string. So you end when you're equal to the string length, and then one if statement, see if character I of your string is equal to a lowercase e, and if it is, increment your count, and then return your count at the end. Despite being able to do this in a few lines of code, there are dozens of ways you can go wrong in trying to do this, right? Lots of little details that can trip you up and be elusive. If you use a while loop, remember you're trying to loop until you get to the null terminator. That's a \0 in single quotes. Okay? Don't try to look until you get to a new line. Okay? If you read a string from fgets, you'll have a new line at the end, but that's just fgets. Okay? If you just pass this a string like double quote hello, there's no new line in there. And if you're looping until you find a new line, there's a good chance you're going to seg fault. And even if you don't seg fault, right, it may not be doing the right thing. So let's play with GDB. So let me write a test program. All right, so here's my own version of a test program. This is not very complete because I'm only testing one string, but let's do this and see what count he does. So I've got county.c, I've got main.c. How do I compile this if I want to use GDB? Okay, gcc-g. -o main.c county.c. Bless you. And then GDB main. So I should be able to list and see all of my code. So GDB can be a little weird when you've got things in separate files. But let's try this. So let's go ahead and start this. So I'm inside, okay, so I'm about to call count E, so I'm going to say step. And I'm inside count E now, and I'm at line 1, and I can list the source code for that. So I'm ready to start stepping through my function here. Let's just do some steps. So it says for I equals 0, I less than string length arg, I plus plus. First thing I'm going to do is print the value of C. And if you forgot to initialize C, this is going to be some crazy number, right? And that's going to tell you got a problem right there. But C is equal to 0, okay? So I'm going to say step, well, no, first I'm going to say let's print out arg. Let's see what that looks like. Okay, that looks like a nice solid string. I'm going to loop for I equals 0 until I is less than string length of arg. Let's print string length of arg, and it tells me that's 5, which is what I'm expecting. So no surprises there. But if there was something in arg that I couldn't see that was making it look longer, right, that might show up there. So now I'm going to say step. I didn't want to step into string length. My bad. I don't know what that means. Okay, let's try next. Okay, so if arg_i is equal to e, so I'm going to print I. I'm going to print arg bracket I, and that's equal to h. So I don't expect this to change c, right? So I'm going to print c right now. I'm going to say next. I'm going to print c. C hasn't changed. So far, so good. Now we're going to do this next iteration. And we're going to print I. And I'm going to print arg bracket I. And that is equal to e. So now I expect c is going to change. So I'm going to print c again. It's still 0. I'm going to say next. I'm going to print c. C got incremented to 1. All right, so this is doing exactly what I hope it will do. So I don't want to do this through my entire string. I'm just going to stop before I return and make sure that c is what I want it to be. So I'm going to say break 8 after I get my connection back. And then I'm going to say continue, and it will run until it hits that breakpoint. And then at that point, I can print the value of c. It should be equal to 2. And then I'm going to say next, which will bring me back to my main program. And my main program was taking the return from this function and storing it into a variable I. And I'm going to make sure that that happens. So I'm going to say continue. I'm about to return c. I'll print c. C is 2. So far, so good. I'll say next, come out of my function, and this thing just did integer I equals count e. I should be equal to 2. So if I print I, that's equal to 2, and now if I execute the printf, it shows me I equals 2. So that all worked fine. But there's different things that you can So this is going to use a while loop instead, and it's going to go until arg_i is not equal to, it's going to go as long as arg_i is not the null terminator. Oh yeah. Yeah, that's intentional. But thanks. All right, so I'm going to step into count E, and now I'm going to start nexting. And if I decide to print the value of I in here, oh, it is 0. Yeah, that's okay. Right, so I'm going to print the value of I. You're going to notice that it's like not incrementing, right? And so arg_i is equal to h, so c is never being changed. But if you just start going through this, right, it's never going to come out of the while loop. Right? Now, if you try to assess this, what happens, it looks like assess isn't playing with you. And you say G to grade, and it never comes back. It doesn't say errors. It doesn't give you a score. It's because your program's in an infinite loop. Okay. And if you step through it in GDB, it'll be really obvious that that's what's going on. Now, if you're not stepping through it, if you say something like, let's just put a breakpoint at line 9 and continue, it's not going to hit line 9, right? And at that point, it's probably too late to debug, so you need to get out of here and go back in and try it again. The other thing that can go wrong is although it's not doing it for me. But the other thing that can go wrong is that since you're not initializing I, sometimes that'll have a crazy value. And it turns out in GDB it seems to be initialized to 0. But depending on the time of day, that may not happen. So let's just put a break at count E. Yeah, so it's initializing it to 0. So that's a problem in the program that's not actually being revealed by doing this. But But if you run it outside GDB, it might actually show up. So that's unfortunate. Let me show you something else that I saw some people doing. And I see this a lot. Right, so I'm running my program and it seems to be stuck. And if I was assessing this, it would be hung. And I'm trying to process this phrase E-I-E-I-O. So let's break inside county. So I is 0. Arg is the letter E. So I'll come down here. If arg is equal to E, which it is, it will go ahead and increment C, so I can print C, and that's a 1. And then it will increment I, and
increments after.
Yeah. And so I is a 1. So now it will say arg I is the letter I. That's not the null terminator. So we'll continue with the loop, and we'll check to see if arg I is equal to E, and it's not. And we're back up to the top of our loop, and if we look at the value of I, it's still 1. And arg I is not equal to the null terminator, and it's not equal to E. And you can see what's happening now. Right, this is our infinite loop, and I is never changing. So you go back to your code and you look at it and you realize the only issue is that I'm incrementing I inside that if statement, right? And if I had put that I++ after that bracket, right, this will work more correctly. So these are easy typos or conceptual issues to make. Let me go ahead and initialize this just to be clean. Right, so now I can run this and it does the right thing. These are easy mistakes to make, right? The idea of using GDB or some other debugger is that it shows you what's happening step by step, right? Memory location by memory location to help you figure out what's going on, and then you can come back and say, oh, okay, there must be some logic error in there. So I definitely recommend starting to work more and more with GDB. And remember to compile, just throw in a -G switch and then run your program by saying GDB program. And use break to set up breakpoints, use stepper next to go one line at a time, use print to look at variables. That's more than 80% of what you need to use GDB. And it feels kind of awkward the first few times probably, but it gets more natural. And then eventually it's pretty comfortable. All right, questions about that? All right, let me talk more about this business of breaking things into pieces. So we've talked about this a little bit before, but let's do it officially now. So you write C code, you've got a file.c, right? That's the human readable version of your program. And normally we just run gcc and we get file or maybe a.out or whatever our executable is, right? But there's steps that happen in between here. So the actual compilation gives us file.o. And that's an object file. it's all of this stuff, right? Integer, numsticks, equals, function calls, declarations. It's all of that stuff translated to ones and zeros. Okay, it's a form that's easy for the machine to ingest. And the way we compile into an object is we say gcc-c. So if I say gcc-c main.c, let me do an ls first. gcc-c main.c, and now I do an ls, I've got a new file, main.o. Okay, that's the object file. And if I look inside there, it's gibberish to us, but it means a lot to the computer. Now it's pretty short. Right, main.o is only 1500 bytes. Main, our executable program, is almost 13,000 bytes, 13,000 characters. Right, but main itself, which was 234 characters of C code, got compiled into this 1500 character object module. Okay, so we can have, use better names. We can have main.c compiled into main.o. Yeah, thanks. So we've got main.c, that gets compiled into main.o. We've got playgame.c, which we can compile into playgame.o. We've got start.c, which we could compile into start.o. And all of these are done with gcc-c. And compilation is kind of an expensive process. We have these programs with big variable names, number of sticks we are playing with, right? Which is ultimately just going to be some location in memory, but we've got this big long name, and the system has to keep track. This big long name means memory location 18, right? We've got all the comments we put in our code, right, that the compiler has to skip over. We've got white space that we put in there just to make it easy for us to read, that it has to deal with. It's got to match up, curly braces to know where things begin and end. It's a fairly time-consuming process to compile from a .c file into an object. But these object files are made for the machine to ingest. So to process those is relatively straightforward. So, and there's other things in here. So these .o files can get assembled into something like main, which is an executable. And that's usually done with a command called ld, which is a loader. But we can actually do it with GCC as well. And if you feed GCC a bunch of .o files, it knows I don't have to compile those, they're already compiled. It will just go ahead and link them together to make an executable. So here's how we could do this, right? We can always compile like this, because I know every .c file in my directory is part of my main program, so I can just say gcc-o main, and then just list all of those star.c's. But that's compiling every one, main.c, playgame.c, showsticks.c, start.c, right? So here's a more staged way to do that. Okay, now I've got 4.0 files. And now I can do the following. I forgot one. All right, so now I can say GCC, call my output file main, and I can give it these object files to link together. Okay, and this is a relatively fast process. This is pulling together the functions that we've put into these 5 files, and it's also pulling in things like printf, fgets, scanf, because GCC knows that I'm going to probably use those functions, and so it goes to a standard library which contains all of these functions, and it looks for any functions that I'm requesting, and it'll pull those in. So there's other things being linked together here, but that's all fairly fast. Okay, everything is set up in these files specifically to make that linking process efficient. Here's the advantage of doing this. So here's my showSticks function. And suppose I decide I want to print out this number in square brackets instead of parentheses. So I'm going to print out pile sticks and then bracket this thing. Okay, that's a really small change to this function, right? If I just say gcc-o main star.c, everything gets recompiled again, right? It's much more efficient if all I do, since this is the only thing I changed, is I just recompile this. And it's a 5-line program, so that's very fast to do. And then I go ahead and I say link all of these objects together. And now I've got my new main program, and it's showing me my number of sticks and brackets. So the whole goal of this aspect of modularizing is efficiency, right? The goal is if you've got thousands of files being put together into a program and you make a change to one of them, you don't have to compile all thousands of files at the same time. You can just compile the one file you change. Okay, that only works if you're keeping everything in these object forms and then just changing the one file, compile it into a new object, link them all together. Does that make any sense? Okay. So if you look inside here, I didn't define any function prototypes. I didn't tell it what start is. I didn't tell it what showSticks is or play game, right? But it didn't complain because I have this one line up here which says include this file stick.h. Okay, so let's be clear what include is. Include is basically saying read this file and plop it in right here before you do anything else. Okay? It's the equivalent of doing this. Comment all this out. Take all of this, pop it in right there. Okay? No difference. Number sign include says take the contents of that file and put it in right here, and then go ahead and compile. So if I put a bunch of include statements here that say include start.c, include userMove.c, include parseArguments.c, and all of that stuff, what's going to happen is before I compile main.c, it's going to take all that C code and throw it into this file. And I'm turning my nice modularized system into one big, long, gargantuan file that has all my C code in it. And then I'm compiling that, right? And I've killed my efficiency now. So we don't want to include C files, okay? We want to include things that we need to type in the top of each file, but we don't want to type in the top of each file. For example, function prototypes. So here's the prototypes for the 4 functions I'm using. I don't want to have to type that every time that I make a new function. So I put it in a single file and I just say include that file. The advantage is if I decide I need a 5th file, like when I first wrote this, I forgot about showing sticks, right? And then I remembered, okay, I've got to print out the number of sticks in parentheses with vertical pipes and all this kind of stuff, right? If I'm just writing these function prototypes in the top of each file, now I have to go into each file and I have to add an extra function prototype for showSticks, right? If I put these all in stick.h and the top of each of my functions says include stick.h, if I want a new function prototype, I can just put it in this file. And when it gets included, it's automatically a part of my new files. So things that you know you're going to do repeatedly, throw into a .h file. right? But not executable code. Just things like function declarations, right? Function prototypes.
How do you make a .h file?
Same way you make a .c. You can just edit it with VI and just type in your...
You don't need to compile, do it?
Doesn't need to compile, right? Because this is really just literally being included at this point in the file. So before we actually compile code, there's something called the preprocessor. You can run it with CPP, the C preprocessor. And one of the things the preprocessor does is basically look at these include statements and just read the contents of stick.h and pretend that everything that's in stick.h was typed right here. Right? So it's really just a plain text file. And you can include anything that you want. Well, let's include haha. Right, so if I don't have a haha, it's going to complain. If haha contains a comment, I can compile, and it saw a comment that said this is weird in the middle of my main.c, which didn't do anything. If I put something weird in there and I try to compile, it'll say, hey, something weird happened at line 6. You said haha int, right? And it didn't know what that meant. Because when I included this file, well, okay, let me just show you something weird here. Right, so if I don't tell it what type of return main is, I get this warning, right? So my file haha could contain the word int. Oh, that didn't work. Okay, scratch that. Oh, I didn't include it. Okay, so my warning went away. So what just happened here? Right, you don't want to do this. This is just a pathological example, right? I'm including this file haha, which contains the single word, it contains a comment and then the single word int. And so it thinks right here I typed the word int, followed by main, right? Followed by the arguments to main, and it thinks I'm declaring main as a function that returns an int, which is what it expects, right? So it's nothing other than just a file, and whatever's in that file basically appears at this location. So I mean, I could take every word of my program and throw it into a separate file and just number sign include all those files and write my program in a really weird way, and it would work perfectly fine. It's just a strange thing to do, but you can do it. But don't submit it to me. That would be fun to grade. All right, so you're getting the idea, right? We're going to take these functions .c files, we're going to compile them to .os, and then we're going to link those together. And the downside to doing this is trying to keep track of everything, right? So how do I know what my .os are that I need to link together? How do I know what the dependencies are? And if I change stick.h, do I need to recompile some or all of these functions? Right? I need to look through these and see which ones actually include stick.h. And show sticks well, this one doesn't actually need stick.h. Right, because I don't use any of those functions. So if I change stick.h, I don't need to recompile show sticks, but I definitely need to recompile main, because that calls a bunch of functions. So keeping track of all of this is challenging. So there's a tool we can use. And this is something called a makefile. And it was probably like 20 or 30 years before I actually started using makefiles myself. So if you don't like totally fall in love with them today, I understand. But let me show you what a makefile does for us. So we're going to call our makefile with an uppercase M. And this is just a plain file, right? Just like stick.h. But it's a recipe for how to create our executable program. And the general format of a makefile is pairs of lines. So the first line says, what's the thing that we're trying to make, colon, what does it depend on? And the second line starts with a tab, and it's got to be a tab, can't be spaces, and is followed by a recipe for making the target. And then there's a target and a recipe, and so on. So let's build a makefile, and then we'll see what it actually does. So the target I'm trying to build is a program called main. And what do I need in order to build main? So let's bring another window over here. Okay, so I need all of these objects to exist. And if I have all of these objects, and if they're all up to date, right, I can build my main program. I can compile them together. So I'll do a tab gcc-o main, and I'll just list all of those object files. So if I say make main, it looks in my directory for a file called makefile. It finds it. It looks for a target named main, because I said make main, and it finds a target here. And it says, okay, in order to make my main program, I need to have these 5 files. And it says, do I have those 5 files? Well, yes, I do. They're all in my directory. And then it executes this GCC instruction to go ahead and build my main program. And it shows me that it did that GCC. Now suppose there is no start.o in my directory, and I say make main. Oh, that's not fair. Okay, so it's doing some of our work for us. Right, so it got smart. It knew that there was a start.c, and it figured out if it could compile that, it would get a start.o. So it's being smart for us. So let's so let's rename start.c. Okay, so now we don't have a start.o, which we've said is in this list of dependencies. So if I say make main, it'll say, hey, there's no way that I know how to make start.o. Okay, and that's needed in order to make main. So my makefile doesn't have enough information. Okay, well, I can tell it how to make start.o. And to make start.o, I need haha.c. And I also need my include file stick.h. And if I have both of those, then I can say gcc-c haha.c dash O. I don't know if I can do a dash O like this, but let's try that. I'll name it back from haha in a minute. Well, I'll name it back now. Okay, so to make start.o, it needs to have start.c, and it also needs to have stick.h, right? And if it has both of those things, then this command will build stick.o. So let me put my start.c back. And let me say make main. And so the first thing it does is gcc-c start.c. That creates start.o, and now it has all the dependencies required to make main. And so it executes this instruction to go ahead and build main. All right, so let me show you a full. So here's my 5 objects that I need in order to build my main program. And for each of them, I'm listing the dependencies and then showing a command that will create that object. And let me just see if I can get rid of any of these dependencies. So start.c, does that need stick.h? I don't believe so. Get user move does not need stick.h either. Play game has to call get user move down here. So I'm going to leave stick.h in there. Main will need that and show sticks does not. All right, so this obviously takes some preparation, right? And this is why a lot of people don't bother with make files, because it's kind of a pain up front. You've got to think about what are the pieces of your program, what do they depend on, and what depends on them. And the more accurate this file is, the better. I could make everything depend on everything, right? And any time that I say make main, it would just recompile everything, relink everything, give me my main, right? But to make this efficient, we want to do as little work as possible when we try to rebuild our executable program. So right now I'm telling it main depends on these 5 objects, and each object depends on a .c file, and a few of these objects like main and playgame also depend on this include file, stick.h. All right, so what does this mean? Well, I can say make main, and it compiles get user move, it compiles start.c, and then it links all of these together and it gives me my executable program main. Now, if I say make main again, it says nothing to do, main's already up to date, because nothing has changed. But let's say I change show sticks, and I'm just going to write it without any changes, but it's going to have a newer timestamp than main. And so now if I say make main, it says, oh, show sticks got changed, I have to recompile that. Everything else is up to date, so now it just links everything together. And if I say vi main, and then I remake, it recompiles main.c. And how is it doing this? when I say make main, it says, okay, here's the objects that I need. It checks the timestamp on these files, and it compares it to the timestamp on main. And if any of these is newer than main, it says, okay, well, if any of these is newer, it will go ahead and rebuild. If not, it checks to see if each of these objects is up to date. So getUserMove depends on getUserMove.c, so it checks the timestamp on this file. If that's more recent than this, it says this needs to be rebuilt. And it'll go ahead and execute this command. And then it goes back up here and it checks again and says, okay, now the timestamp on this is such and such, the timestamp on main is older, I need to rebuild. And if you don't say make something, if you just say make, it takes the first target as the thing that you want to build. So I can just say make, and it'll always try to make, in this case, main. So all of the difficulty of my compilation and linking and everything else is now a forward command, make. Right? Once you have this file set up. And here's the glorious thing. Suppose I change my include file, and I say make, it knows which C programs have to get recompiled because they include that .h file. So it recompiles those, and then it links everything together, and I've got my main program. And if I say make again, it's up to date. So this can become like, you know, when you're bored, you just say make. It's kind of like saving your file every 5 seconds when you're editing. You can keep remaking your image, and if everything's up to date, it doesn't do any work. And so typically when you download software online, you get a bunch of source files in a tar file, but you also get a make file, right? And the make file contains the instructions for putting all of this stuff together. And then ideally, theoretically, you've downloaded a package to, I don't know, add voice capabilities to your program, and you want to install it on your system. Theoretically, all you have to do is download it, untar it, say make, and hit enter. Come back in a few hours and it should be done. This is how you build a Linux kernel. Right? If you want to update your kernel, you basically download all the source files. There's a make file somewhere, you say make enter, and it'll do, you know, several hours of compilations and links, and at the end, hopefully, it leaves you with an executable target. Doesn't always work that nicely. But that's the mechanism. And make files can get really complex, right? You can add all kinds of things to do it. It's got a whole kind of like programming environment inside almost, which lets you do all kinds of crazy things. But let me just show you one example, which we typically find. We don't need to do this, okay? But it's an example of something we can do that has nothing to do with compilation. I can make a bogus target called clean, and I'm not going to list any dependencies, and my recipe for how to create this target is going to be to remove all of these .o files and the main program. So what the heck does that mean? If I say make clean, it's going to say, okay, here's a object called clean, that's a target, has no dependencies, here's the instruction I execute to make this target. It's going to go ahead and run this instruction for me. And what's that going to do? It's going to remove the results of all my GCCs in this directory. And this is useful, for example, if you're giving a copy of your directory to somebody else on a different machine, and they want to build an executable on their hardware. If they say make, it's going to say target up to date, right, if you already gave them a copy of make. But they need to recompile it because they're running a different hardware system from you, and the only way to recompile it is to get rid of all of these things that you already compiled and gave to them. So now they have to remove star.o and hope they don't accidentally remove something else that shouldn't have been removed, and so on. So you give them a target called clean that basically hardwires the instructions for how to clean everything up. So here's what my directory looks like right now. If I say make clean, it removes the necessary things, and now I'm back down to just my source files, my .h file, and my make file. And now if I say make, it recompiles everything. So if I'm running this on an ARM processor instead of an x86, now it's recompiled using my version of GCC. It's got objects that my system knows, and I've got an executable I can run. And sometimes if you're superstitious and things are just not working well, you go ahead and clean everything out and recompile. Sometimes it works better.
And you just made the makefile by doing the vi makefile?
Yep. Yeah, it's just a plain text file. The only trick is these lines, these recipes have to start with a tab in column 1. And if you just put in a bunch of spaces, it doesn't work. It's a little annoying that way. All right, that's makefiles in a nutshell. We'll talk about something else tomorrow.